And here we are. It's the Physics 203 video lecture. Physics 203 video lecture 4. And we ended last time with the catenary. That's a great example. I think I'll say a couple more words about it. A couple more words about the variational calculus, and then we'll move on into physics. So the catenary, that's the shape that a chain takes. And I don't have the chain with me today, but maybe we have one backstage. Maybe I'll show you the chain next time. But you can imagine, you're holding a chain and it's suspended, and it takes on various shapes. It can take on this shape, or it can take on a shape more like that, depending on how you hold it. And in fact, your solution to the catenary problem will include implicitly the fact that this curve here is the same as this section of this larger catenary, right? Mathematically similar. This here is similar to that. And some applications before we move on. So I'm pretty sure I was adequately thorough last time to set up those two problems. One of them using Newton's law, and the other one using a variational principle, namely that the variational principle was that the potential energy is minimized in the hanging chain, and Newton's law, the principle was that the force is always tangent. Right? The force is always tangent to the curve. That's why up at the upper bound there, it was dy dx. So those are both equivalent when you've shown both of those calculations. You see they're equivalent. So let me say a word or two about an application. The first one is kind of fun applications. If you, say you suspend a chain like this, you get that nice smooth curve, and then you can actually trace it out and get the perfect curve, and then draw a couple of towers here, and then you realize that you're going to have to anchor this on this side. Otherwise the towers will be pulled in. Put a road bed here. And of course, in order to suspend the road, you have to have these verticals, and then you have your suspension bridge. So the suspension bridge is suspended from this giant curve, which in the first approximation is the catenary. Before you hook up the road, it's the true catenary, and then afterwards it'll deform into whatever shape it has to. But that's a good example of the catenary, and then the road comes out this side as well. Okay? And then you've got some water going through here or something. So that's one application, is the suspension bridge. The other one is a little less immediate, but the other application comes from this one right here. I'll just use this picture. So imagine you have a chain, you get this exact shape here for a uniform mass distribution, and you make this rigid. Okay? If you make this thing well, first of all, before it's rigid, it's just a chain. The principle is that the tensions are all tangential. Okay? Tangent tensions. That was the principle here. So if you make this thing rigid, you can stand it on its feet, so to speak. So I'll just send that over here. You stand it on its feet, and you have this shape here in which the compressions are now tangent. So these compressions all go along the shape of the curve itself. There's no tendency to buckle. The gateway arch in St. Louis is based on this principle here. Okay, so the tensions are tangent here. Here the compressions are tangent. So compressions are tangent Therefore, it's not in a buckle. And the example here is the gateway arch in St. Louis. Okay. So there you have it. There's some nice applications of the catenary. And next I want to give you a variational calculus assignment. And what we're going to do is add a derivative. So let's say we have phi is equal integral f, which is a function of y, y prime, and y double prime. Oh, yes. We'll just do this for one variable, that's fine. Okay. Y, y prime, y double prime, x, dx, x1 to x2. Okay, our original problem just was a function of y and y prime, and that's, as we're going to see, that actually suffices for all the physics we're going to do. But this is just an extended version. So we're trying to minimize phi. We're trying to find the function y equals y of x, y prime equals dy dx, double prime, d squared y dx squared. We're trying to find the function y that minimizes this, but our problem involves first and second derivatives. Okay, and what we want to do is find the Euler-Lagrange equations for this type of problem. Now when we vary this thing, so e equals 0 implies Euler-Lagrange equations. But what do they look like? And it's going to be interesting because the case that you discover, if you let y double prime not be present, of course you're going to get the Euler-Lagrange equation we already know. So that'll be you'll be able to test your limiting case that way. So let y tilde of x be equal to y of x plus epsilon g of x, and the requirement what we have to require now for g of x with g of x1 equals g of x2 equals 0, that we already had. We also have to require that g prime of x1, g prime of x2 equals 0. Okay. And then, so this is homework. So the homework is, so the next step, we've set this whole thing up. Should I put some words here? Yeah, y is the function where y of x is the function that minimizes phi. So you're doing the same thing as we did in the other case, phi of epsilon, just the way we constructed it last time, except there's more in there. And then d phi of epsilon, d epsilon, evaluated at epsilon equals 0 is equal to 0. That's an interesting calculation. You'll see, because it makes you repeat the one I did, but you've got this extra expression here, and punchline basically, you're going to have to integrate by parts twice, where the first time you just had to integrate by parts once. Okay, but it all comes out. All comes out. Good homework problem to wrap up the variational calculus. So with these examples that we did, the catenary, shortest curve type of problems, and then this formal one again, we're in good shape. So now we're moving on to physics, to Lagrangian mechanics. And we inherit this whole formalism that we have developed. So I'll go ahead and write that formalism down on the left side of the board, and then write the physics part on the right side of the board. Okay. So for our variational calculus, here on the left side, we had variation of an integral of the form f of y1 to yn, y1 prime to yn prime in x, dx, fixed boundaries, equals 0. And if that's the case, then we have two things. We have the Euler-Lagrange equations, d over dx, partial f, partial y sub I prime, partial f, partial y sub I, equals 0, I equals 1 to n. And the other thing we have is Euler's second form. Euler's second form, which is that the sum partial f partial y sub I prime times y sub I prime minus f is equal to a constant. Okay. This form of Euler-Lagrange equation simply comes from the fact that we varied y sub 1 to y sub n independently. Okay. So if you do the calculation for one variable, you don't even have to do any more. I'll just remind us, because we form a phi of epsilon 1 to epsilon n as a minimum at epsilon equals 0. That's enough to turn that original calculation into this many variable version. And this independence of these variables is very, very important. Okay. And then this constant property just makes use of the Euler-Lagrange equations, and in fact what we're going to do is rediscover this in its physics form pretty soon. So now I'm going to translate this to physics. So in physics we have what's called the principle of least action. Remember, we derived that principle of least action earlier. L dt t1 to t2 is equal to 0, where L is equal to t minus u. So what we did was we developed what this formalism meant, which was a bit vague at this stage. We got a very concrete development of what it meant. And now what this principle of least action means, principle of least action, that's covered by the steps we took to get these variational equations. So now we can just translate them. In Cartesian coordinates, for starters, Cartesian coordinates, when we have system with point masses, that's where we'll start. Then the Lagrangian kinetic minus potential energy has the form 1/2 m sub I r sub I dot squared minus u of r1 to rn, right? if there were a plus sign there, that would be the energy that we had found was conserved in the past, okay? So that would be our Lagrangian, the Euler-Lagrange equations, basically taken 3 at a time. I'm going to write them down. I'm going to write these Euler-Lagrange equations down 3 at a time because I have these vectors, which are 3 coordinates at a time for each ion particle. I'll also erase this. Okay, so now d dt partial L partial R sub I dot. That's the translation, right? There's the derivative y prime R dot minus partial L partial R sub I equals 0. I equals 1 to n. And does that turn into Newton's law? It does. Because dl dr dot are, you know, let's go ahead and use a k here. I always want to use a different subscript. K equals 1 to n. Okay, so we'll go with respect to the kth one, we're picking off the k there. So this is d over dt dl r sub k dot, go ahead and write what that is. That's m sub k r sub k dot. This is the derivative. You pick off kth of these, the r dot squared. There's a linear. Those are 3 equations, right? And then minus. So dl dr sub k is negative gradient sub k of u. Equals 0. M sub k r sub k second derivative equals minus on minus is plus. You get a minus gradient sub k of u. Of course, that's Newton's law. Okay, so check that off. We have Newton's law in Cartesian coordinates. Of course, if that's all we get out of this, we wouldn't have gone through the trouble, right? Because that's what we started with at the beginning of the last couple lectures ago. But it's a consistency check. Also, if we're going to translate this thing here, we have the sum of dl prime goes down there. Good save, right? So the sum of dl r sub k prime r sub k is r dot minus L is equal to constant, which is to say that the sum of m r sub k dot dotted into r sub k dot k here, and then the L is outside is equal to constant. So this is what we inherited. We have this, we're going to see soon, this is the conservation law, and we have these Euler-Lagrange equations. So this pretty much covers the point mechanics, okay? So, as in Newtonian point mechanics. Of course, that's what we started with, that's what we have to get back. Okay. So the next thing we're going to do is extend this to different applications where we get more out of the principle than just the point mechanics. Okay, time to check the time. Alrighty. Okay, so we do have this variational principle And what's important there is that L is a scalar. L is a scalar, and because L is a scalar, we're just trying to minimize this expression. We can express L in terms of any coordinates we want to, as long as they're independent coordinates. And that's the big advantage here. If we express the Lagrangian in terms of the most useful, convenient coordinates, then we will automatically get the correct equations of motion out. And these coordinates are referred to as generalized coordinates. They're not really anything new. Generalized coordinates will right from the outset be plane polars, spherical polars, cylindrical. But we'll see that it does go beyond that, because we can often mix Cartesian and angular coordinates as needed. Good. So I'll send this up here. As soon as we set up some generalized coordinates, then we'll set up some basic problems in mechanics that we want to discuss, as well as touching base with any old problems that we've already done. Okay, so generalized coordinates. And I'll put this as a comment. This variational principle, T1 to T2, where L is a scalar, means that we can use any coordinates that the Euler-Lagrange equations are correct. Right, they give the correct equations of motion for any choice of coordinates. For any set of independent coordinates. And the point is because it's scalar. Okay. So we're going to define the generalized coordinates. Define generalized coordinates are any set of quantities that determine the position of a system. Let's see. Any set of independent quantities that determine the position of a mechanical system. Mechanical system. So the independent and position are really crucial here. I think the first example, the simplest one, let's talk about a plane pendulum. Mass at the end of a massless rod or string. So this thing lives in two space. Okay. So we've got X and Y. But we can't let X and Y be generalized coordinates because they're not independent, because this thing is constrained to move on this arc here. So X and Y are not independent. So they don't count. Okay. What you can do is use the angle. And then you can say, well, this angle uniquely determines the position of this pendulum here, theta, say you want to restrict it between plus and minus pi over 2. Okay, it's well determined, and that's your generalized coordinate, and then you apparently only have one generalized coordinate. Angle theta does the trick. Okay. And I'm going to go straight to one of our examples that we'll be working with. So suppose we have, what I'm going to do is I'm going to combine a pendulum with something else. So our second example is we have a frictionless track here, and we have a mass on a spring, capital M, spring constant K, x-axis, and we suspend a pendulum of mass lowercase m, length L, from this mass on the frictionless track. So this thing can move back and forth on x, and this thing can swing back and forth. And we'll generalize this as well, but this is a good one to work with. So now, same thing holds true. You can't have x and y here, because there was just 1 degree of freedom. But on the other hand, this thing is moving forward and backwards. So the position of this pendulum is going to depend on the position of capital M. So what are the independent coordinates? You could say x and theta. Am I using theta? Yeah, x and theta are independent generalized coordinates. Coordinates. Okay. Independent generalized coordinates. And this one we're going to actually construct. We'll construct this one, and I'll give you a slightly more complicated one to work with. So x and theta are independent generalized coordinates, but we have to find the Lagrangian t minus u. Okay. So now find L equals t minus u. So how do we go about doing that? All we know about potential and kinetic are fundamentally in terms of Cartesian coordinates. Okay. So we could have t equals 1/2 capital M x dot squared, and I'm going to use a capital X for this coordinate here. The capital X dot squared, and then you could say we have a 1/2 m lowercase x dot squared plus y dot squared for this one here. But this could not go into the Lagrangian in this form. Potential energy, we could say, is a 1/2 k capital X squared plus negative mgl, actually getting ahead of the game here, plus mgy. Okay. But again, t minus u here would not be a Lagrangian. These are the points of, this is what we start with to construct it. What we're going to do is transform both of these with lowercase x equals uppercase x plus L sine theta, as you can see here. Right, it's whatever capital X is plus this little distance. And then lowercase y is equal to minus L cos theta. And now we have to square x dot and square it. So we have x dot equals capital X dot plus L cos theta. Theta dot, chain rule, right? And y dot is equal to L sine theta, theta dot. And now we'll get the x dot squared plus y dot squared for this. Plug in the appropriate mgy put everything together, and then we'll actually have the Lagrangian. So I'll go ahead and work right under here. Should I give this as a homework? Well, let's work. Let's keep doing this together. Okay, so what do we have? X dot squared plus y dot squared equals capital X dot squared plus 2L cos theta. Theta dot capital X dot 2L theta, yeah, plus L squared cosine squared theta, theta dot squared, L squared sine squared theta, theta dot squared. Sine and cosine squared equal 1, so we get plus L squared theta dot squared. So now we have the ingredients to get that Lagrangian. L is equal to 1/2. Now we're going to have M from here and M from here, okay? So we will have a capital M plus lowercase m on the capital X dot squared. I'm going to put this in a certain standard form right away. We're going to have a 1/2 m L cos theta X dot theta dot plus a 1/2 m L cos theta theta dot X dot. You notice I distributed this. I had a 2L here, and I distributed one of them here and one of them here. Okay. That all comes from that term plus a 1/2 m L squared theta dot squared. That's my kinetic minus this potential. I like to factor out the minus sign because I'm just going to end up with minus mgl cos theta. There's my potential energy. Not so fast. Minus 1/2. Maybe I want to do it this way. Minus, open parentheses, 1/2 k capital X squared minus 1/2. The 1/2 is wrong. Minus mgl cos theta. There we go. So there's the Lagrangian of this thing. And you know, this looks pretty complicated, and it is, but it's the simplest way to get at this system here. Good, so there's a 2. I'm going to place some parentheses here already, because when we get into the standard form of this, it'll be important, okay? So these parentheses were already placed, these blue ones. It's always the form of a 1/2 times something times your variables, your dynamic variables. Okay, so there's the Lagrangian of that system. Yeah, should I put some homework problems up there? Okay, so I constructed this one pretty systematically. What I want to do next is get this construction in general form, because we're going to be working with a general Lagrangian that is not Cartesian, right? We need the Lagrangian in generalized coordinates. This was an example, an adequately complicated one. So next we want just the Lagrangian in a system of generalized coordinates. Okay. I'll send this one up here. Yeah, this next one is a bit of a construction. And in fact, before I do it, I'm going to write down the Lagrangian and plane polar coordinates. I put them right under here, so I got plenty of room. Because that way we'll have some good examples, concrete examples. So plane polar coordinates. Let's also do this one first, and then we'll do the general case. So what you're looking at is x equals r cos phi, y equals r sine phi, right? In plane polar coordinates. And you want to get the Lagrangian for a point particle in plane polar coordinates. You get your x dot r dot cos phi plus r negative sine phi phi dot, time derivative, and y dot, this is all chain rule and product rule, r dot sine phi plus r cos phi phi dot. So when you sum and square these, you do x dot squared plus y dot squared equals, you get the r dot squared, cosine squared plus sine squared, so it's going to be r dot squared. Then your cross terms here, r dot r cos sine and phi dot, and r dot r sine cos and phi dot. The cross terms go away because this one has a minus sign, so you're left with plus r squared phi dot squared. Okay, sine squared plus cosine squared phi dot squared. So from this calculation, here is our Lagrangian that we want to use. Have n r dot squared, r squared, phi dot squared minus u of r and phi. This is very general for plane polar coordinates. This was for that somewhat complicated system. Okay. Yeah, because this one we can always refer to. Okay, so now the general form of the Lagrangian. Lagrangian generalized coordinates. And the generalized coordinates are q sub 1 to q sub n. Now the example with plane polar, coordinates, you know, we have x equals r cos phi, and our q's are this r and this phi. So we could say q sub 1 is r, q sub 2 is phi. Okay. So we're going to transform from Cartesian to generalized coordinates, just as we transform from Cartesian to plane polar coordinates before. So that transformation would be x sub I is equal to f sub I q1 qn. This was an x sub 1, q1 and q2, x sub 2, q1 and q2. That's the idea. So x sub I is f sub I of q1, qn. T is equal to 1/2 sum over m sub I x sub I dot squared. You know, if you're thinking point particles, then you've got m sub 1, x1, x2, x3, and then m sub 2, 4, 5, 6, and so forth, okay? But that's no problem. We're always just going to say I equals 1 to n. Okay. N, 3n makes no difference. Okay. Good. So this is what we have, and u is equal to u of x1 to xn. This is our Cartesian. How do we get it in terms of these q's? So now we're going to write x of I dot is going to be equal to, by a chain rule, df sub I dq sub j q sub j dot. J equals 1 to n. Okay, that's just the multivariable calculus chain rule where you just sum over all those individual chain rules. Okay. And if we want to square it, this is the key to this whole thing. If we want to square xi dot, and we do, we write this sum out dfi dqj qj dot. Okay. But we don't just square this now. We write it again with a different subscript, with a different index. So k equals 1 to n dfi dqk qk dot. So that's how we square xi dot. Looks a little complicated, it's about to get worse, but don't worry, there'll be a satisfying conclusion to the whole exercise. Okay, so now we're going to form this expression here. This one will essentially be trivial. We'll just say u is u of x sub I of q sub 1 to q sub n. Okay, so it will just write it out without changing the name of the letter. This one here we have to do a little bit more. So now t is equal to, let's just do the definition, 1/2 sum over I, m sub I, and now we have to plug these two in, sum over j, partial f sub I, partial q sub j, q sub j dot, sum over k, partial f sub I, q sub k, k dot. Looks bad. 3 sums. I'm just going to rearrange them. 1/2. So the sums over j and k go like that. And then inside here, we will have sum over I, m sub I, partial f sub I, q sub j, partial f sub I, partial q sub k. And then outside of that sum, we have the q sub j dot, q sub k dot. Q sub j, q sub k dot. This is the kinetic energy. Important point now. So this looks so complicated, we're just going to give it a name. Aij of q. Because it turns out it is a function that only depends on the coordinates. Okay? Aij of q. And we'll see in a couple of our examples in a moment, there's no problem with it. Okay? Not difficult to think about. And what that does is that turns the kinetic energy into a very general quadratic form, a positive, definite quadratic form. That's something we see again and again and again. So here's what we've arrived at. Yeah, I'm so... Okay, I'm going to have to erase this and it's going to be gone from my memory. But I'll assign something right away, okay? So hold on to this. I'm going to erase it. plane polar coordinate. This one I'll leave here and refer to this next. Okay, I need some room. Good. Okay, perfect. So here's what we have. T now L is equal to, we have 1/2 double sum JK AJK of Q QJ dot QK dot minus U of Q1 to Qn. Because each of those x of i's was a function of the q's, so you just transform that function, no big deal. So this AJK of Q often causes people a little concern, but if we take this example here, we can see it's no big deal at all. So I'm going to write this one out. I'll just continue this. It's 1/2 m r dot squared plus 1/2 m r squared phi dot squared minus u of r and phi. So what is this aij, or a sub jk of q? It's an n by n matrix. We could write it out as an n by n matrix, but it's just the coefficients here. See, you've got your 1/2, you've got these coefficients, you've got the generalized velocities. So here for the plane polar, this is r dot, so that's Q1, Q1. It's got an m there, has no mixed terms, no r dot phi dots, we've got a 0, and here it's got an mr squared. See, so this gives us a great little homework problem from what I just erased here. Homework. Write out aij of q for the mass and pendulum system. So the mass and pendulum was this guy, right? Is that one. So you want to write out that 2x2 matrix for that one. Notice it's going to have the off-diagonal terms as well. And you'll notice when I wrote it down, I actually factored out in blue, or I factored out the coefficients. Because the general form, it's 1/2 some coefficient, that's this thing, times your generalized velocities, your square terms. Yeah, so that's what this thing is in general. And when we do theory of Lagrangian mechanics, we'll often just throw this thing up there and talk about it, okay, for the general type of systems. That's why it's so important. So let's do some property. I'm going to erase this now. Let's do some properties of this a sub jk. So I'll just put these down as notes. Note, kinetic energy is a positive definite quadratic form. Positive definite quadratic form. That's some terminology. That's what this thing is. It's always positive. And it's a quadratic form. It's just a sum of every possible quadratic form, possible term here. So if you're not used to these kind of things, you know, you could have t is equal to 1/2 a11 q1 dot squared plus 1/2 a12 q1 dot q2 dot a13 q3 dot, and so on, and then you'd add 1/2 a21 q2 dot, 1 dot, right? It's just bookkeeping. So that's the first thing, definite quadratic form. You can think of this A sub jk as a positive definite matrix, okay, if you want to. So that's the first point to be made. The second very important point is that A jk equals A kj is always possible. You can always make the thing symmetric. In my example with this system here, I explicitly turned it into a symmetric matrix. So look at this example. So it's always possible for it to be symmetric, and you make it symmetric as you're constructing it. And I'm talking about the symmetry. Positive, definite, and symmetric. And with these examples, plane polar coordinates in our complicated system, we're good to go with this object here. So there's our general Lagrangian that we're going to talk about, or that we're going to use for various and assorted discussions. Okay. Let's see how we're doing for time here. 50 minutes. Yeah, we'll go a bit longer. Okay. Yeah, before I get into conservation laws, let's do a couple more Lagrangians and just spend a little time with the equations of motion. Now, the one for this system here, we could write out the equations of motion, but the one point to be made is they're already more complicated than you'd really like to write out, unless you absolutely have to. But I will do the plane polar coordinate Lagrangian for the central force, because that's one where it's simple enough to write out. Okay, so now that we have this, let's see. Do the general form of the Lagrangian. Let's just go to some Lagrangians now. We have a couple already. Some Lagrangians. We want to do the most basic ones just so we can write them down. So, simple harmonic oscillator. How about that? Simple harmonic oscillator, and we think of that as being, we're on the x-axis here, mass in a spring. Okay, mass in a spring, no friction. So L is equal to T minus U, 1/2 mx dot squared minus 1/2 kx squared. And what you want to do is write out the equations of motion. I'll just put this as homework. Write out Euler-Lagrange equation. There's one of them, and of course, it will give you the equation of the harmonic oscillator. Okay, it was long, but that's a good one to start with. The second one, we'll do projectile motion. Right, all of our classic systems, we definitely want to be able to do in Lagrangian mechanics. So projectile motion, we'll imagine that x, y, and z are our coordinates, and g is pointing down in the z direction. So now we have L equals T minus U, L equals 1/2 m x dot squared plus y dot squared plus z dot squared minus mgz. It's our Lagrangian. And again, go ahead and write out the Euler-Lagrange equations. Okay? Right, there's really familiar things that you definitely want to make sure we had those. So, simple harmonic oscillator, projectile motion, and my third example, take a little more room for that. We want to write out the central force Lagrangian. We're going to do central force problem in some detail later in the semester, but for the moment, we'll just write down what we had before. So, actually, before we get to that, how about simple pendulum? Simple pendulum, there's a mass on the end of a massless string or massless rigid rod. Here's an angle theta. So we just had the plane polar coordinates kinetic energy, and here we're going to restrict R to being a constant, so we have L is equal to 1/2 mL squared theta dot squared, and we're calling this the positive direction. G is pointing down, so minus negative mgl cos theta. So that's our simple pendulum Lagrangian. And here let's also write out the Euler-Lagrange equation. And finally, let's do this plane polar coordinates. No, central force. So central force, so what does central force mean, first of all? It's that if you have two particles, say gravitating particles, the force is along the line joining them. And in the central force problem, we'll reduce that to a separation distance r, and therefore the force will be generated. Central force F is minus gradient U of R. Okay, we'll do that systematically when we do the central force problem systematically. And then after several steps, we'll get here, several more steps, we'll get here. L is equal to T minus U, 1/2 m R dot squared R squared phi dot squared minus U of R. So that's your general central force Lagrangian. And we'll write out the equations of motion for this. Equations of motion. Now here, since we have all four of them up here now, one equation of motion, here there are three, Q1, Q2, Q3, that's X, Y, and Z. Here there's one equation of motion, and here there are two equations of motion. So you write them all out, you've already gotten some practice. Good, let's check our time once again. Okay, so we're running about an hour. So how do we want to wrap this up? We got some Lagrangians, we got a bunch of systems, equations of motion. Yes, I'm going to get one more important feature here that will give us everything in terms of the formulas. Okay. So we had that conserved quantity, we had that constant quantity that we inherited from the variational calculus. I have not yet characterized it. So I will do that. This is worth it. It's a fairly involved calculation. So this is the Lagrangian we're working with. We're working with this general one. I'll write it down again for me. So let's see. Yeah. So here's the thing. We now have L is a function of Q1 to Qn when we have our generalized coordinates Q1 dot to Qn dot. Potentially also T, although we probably won't do any time dependent Lagrangians this semester, but we can. They're important to keep in mind. So that's the form of the Lagrangian we have. We know that there's a variational principle that gives us two things. It gives us these Euler-Lagrange equations, dl dq sub I dot minus partial L partial q sub I equals 0. This is the fact you need to do those systems 1 to 4, right? Euler-Lagrange equations in terms of these coordinates, generalized coordinates, and we have this principle here, dl dq sub I dot q sub I dot minus L equals constant. We inherited this from the variational calculus because we just translated. At first we translated into Cartesian coordinates, now we just keep translating to generalized coordinates because variational calculus principle with a scalar. So that's what we have. By the way, if I hadn't said it before, these are the equations that you're going to apply to those Lagrangians 1 through 4. Okay. These are the equations. Now, this thing we have not yet worked with. Okay. So I'm going to derive what this thing actually means, and then we'll have a good place to stop. So this will take about one board. It's not that bad. It's also a kind of a stereotypical calculation that we use more than once this semester, so this is a good time to do it. So this construction of that expression star right there, we start with what is partial L with respect to Q I dot. I. In that, oh, I just erased my Lagrangian. That's nice. 1/2 sum J sum K Q J dot Q K dot Q. Gotta have this thing to look at. Okay. Subscripts are, the indices are J and K. So with respect to Qi dot, we can go through both sums. And we can also go through A and J, K of Q, because it's not explicitly Q dot. So now we're doing D, D, Q, I dot of this Q, J dot, Q, K dot. So yeah, we have to do this once and for all. So this here, you can say, you can hold the K constant, and then you're going to have a Kronecker delta Ij when you're differentiating I, Qi dot, Qj dot, and then Qk dot. Or you hold the Qj dot constant, and then you have a Kronecker delta Ik. So when you go to the summation with the ij, you're getting rid of the j sum. When you do the delta ik, you're getting rid of the k sum. And so what we have here is 1/2 sum over k, a sub, now you replace j with I, so a sub I k q k dot, and you do it again. Now you're holding j, you're getting rid of the k sum because you've got q, j, you've got a with this Kronecker delta here, Kronecker delta I k, so j I, a sub j I q j dot. Okay. So that's what this differentiation with respect to q sub I does. And now we're making use of the fact that the a sub I k and a sub j I are equal or symmetric. These are symmetric matrices. So I'm going to get rid of this j. I'm going to call this plus 1/2 sum over j a I j q j dot. And then you see I have a I k q k dot, I j q j dot. So these are summation indices. So these two sums are the same, and I can add them up to 1. So equals sum over a I k q k dot. Got rid of the 1/2. K equals 1 to n. Okay, so that had to be done, and now we did it. And we'll do it a couple more times in the semester, so it's a pretty standard operation. Now we can form this. Okay. So now, sum over I dl dqi dot qi dot minus L is going to be equal to sum over I, sum over k, a I k q k dot, and then I've got the qi dot here. I'll even put parentheses around it, qi dot minus L. But this is 2 times the kinetic energy. Right? It's the same expression except it doesn't have the 1/2 in front of it. So what this is 2 times the kinetic energy minus T minus U, which is this L here. So this is 2T minus T, minus is plus U, equals the energy, total mechanical energy. That is our conserved quantity that we inherited from variational calculus. In the case of Lagrangian mechanics, that is the energy. But there's an important note I have to finish with. Having done this calculation, it required that L not be explicitly a function of time. Okay. That's how I write that. L is not explicitly a function of time, i.e. L is simply a function of the coordinates and the generalized velocities, then sum of dl dq I dot qi dot minus L is equal to a constant. That's the conservation of energy right there. We'll talk about it again in the context of the conservation laws in general, but right now it is another important equation if you're actually trying to solve problems. It's as important as energy conservation ever was in trying to solve problems. And it depends on L not being explicitly a function of time, because that's where Euler's second form came from. Good. This is a good place to stop. I assigned a bunch of elementary things, just to writing out some equations of motion. And next time we'll pursue more mechanical systems on the one hand, and the conservation laws. I think, in fact, we'll do the conservation laws because we're kind of in this theoretical vein, and once we have everything in hand, then we'll tackle some systems again. I think that's the best way to do it. Okay, good. See you next time.